Okay, let's tackle some more of the questions on the week 3 individual assignment. So I've got the Jupyter notebook for the week 3 assignment here, and I've also got this example notebook from the TMP, is our TMP 36 noise Gaussian. So let's take a look at the content of the assignment. It's asking, is sinusoidal noise Gaussian? Electrical noise from radio frequency emissions and the AC current flowing in your household circuits is a huge source of noise. No surprise there. And suppose the dominant source of noise in one of your measurements is a small voltage around plus or minus 10 millivolts from the 60 hertz AC current that we've got flowing in the wiring. So the measurement, let's assume the measurement's steady for now. We're just going to look at the noise. What would the distribution of the noise look like if you made many independent measurements? So we could look at how the noise changed over time. And the question then is, would it be reasonable to model it as a Gaussian? And why does the distribution look the way it does? So first we need to create a sample of the noise. Well, we'll start off almost as always by setting some temperature value equal to a linear space in time. Let's take 10 seconds worth of data. So we'll go from 0 to 10 seconds. And let's make sure we've got lots of samples, so I'll take 10,000 samples. So we saw before that maybe having a value n that we could change and move around made sense. So let's make n equal to 10,000. So if I run that, that looks like it ran okay. So what's my noise going to look like? My noise is going to be equal to, well, it's something sinusoidal, right? Because it said right up here that we're looking for sinusoidal noise, and it said that dominant source of noise, yeah, so let's make it sinusoidal dependent on time. And then I'll plot the time on the x-axis and the noise on the y-axis and see what I get. And I got an error. Whoops, of course I got an error. I need that to be on two separate lines. And we saw before that needs to be the numplot version of sine in order for things to work out. And I've got a stray parenthesis there. So now I ran it, it worked, and I got a plot of sinusoidal noise varying. Well, one cycle is taking about 4.5 seconds there. So that's probably not, or hang on, one cycle up, then down, then back up again. Oh, it's taking a little over 6 seconds there. In fact, it looks like it's taking 2 pi seconds, which is what we'd expect. But we wanted it to go up and down every 60th of a second. So if I took time and multiplied it by 2 pi, then let's try running it again. So now it's going up and down once every second. If I wanted it to go up and down 60 times a second, then I'd have to have even faster in there, so I'd have to multiply times 60. And it's going up and down really, really fast. So let's just go from 0 to 0.5 here. Maybe we can see what's going on. Okay, yeah, that looks, I believe that's going up and down 60 times a second. So that makes some sense to me. So I've generated some noise. It's really well organized noise. It's coming from AC line voltage. I wonder how much of the time it spends at each of the values between, oh, hang on, -1 to 1. That's not what we wanted. We wanted plus or minus 10 millivolts. So if I wanted this noise to be a voltage that went from 0 to plus 10 millivolts and down to minus 10 millivolts, then I'd have to make that 0.01 volts. So that's 10 millivolts times NP sine, yeah, that should do it. So now I've got it going from negative 10 millivolts up to positive 10 millivolts. And I'd like to know what the distribution is for all the samples. I've got a whole lot of data points here. How are they distributed over that range? Well, let's look back and see this one. This is the one where it's the example asking, is our TMP36 noise Gaussian? And what we've done here in this one is imported some data from this really large file of tmp20.csv, and then we've made it into a floating point array of data. And this example is out there as part of the assignment file set. And then if I plot it, so this is just plotting what I've got time for the temperature from the TMP36, and we saw it warmed up and then it cooled down. So let's take a chunk out of here where it's got a fairly constant temperature, and so I'm just going to take stuff from the last half of the data set and plot it out just to make sure I've got the right thing. So that looks like it's still dropping down a little bit, but it's close to constant. We could at least look at what that distribution looks like. And to find out what it looks like, I can plot a histogram of it. So let's try running that. Plot a histogram. And I get a value set that looks something like this. But it's in fairly fat bins. So I can now try plotting it with 20 bins and normalize so that it sums up to 1. If I do that, this is the histogram that I get. It's looking a little smoother there. That looks a lot more like it's got a Gaussian shape. Now, if I wanted to test that to see if it was Gaussian, then I could compare it to the Gaussian normal PDF function. And let's try that. So I'm doing the same thing. I'm plotting the histogram, and I'm finding out what the mean and standard deviation are of that chunk of data. And now I'm going to plot norm PDF for that mean and standard deviation and see if they look the same. Excuse me. So let's try that one. And because I've already done this, and it's in the example that's in your files, we can see that the orange line here, that's a Gaussian PDF with the same mean and standard deviation as this blue histogram data that we got from the TMP36. So from this example, I feel pretty confident concluding that the noise on my TMP36 can be reasonably well represented by a Gaussian distribution with the same mean and standard deviation. So that's the example that's out there. Let's see if we can apply some of that to your individual assignment. We've got this data. How would we plot a histogram for that data? Well, let's add a cell below this. So I'm adding a cell, and plot hist was the function we used before, and we wanted to plot a histogram of all of our noise, what happens now? Oh, we got this histogram. It's going from minus 10 millivolts up to 10 millivolts. And it seems to be low in the middle and high at the outsides. That's definitely not Gaussian. So I'm not sure we even need to plot a Gaussian distribution on this one to say it's not Gaussian. Now I'm going to look for you to actually answer the rest of the questions that were up here. Would it be reasonable to model it as Gaussian? I think we know the answer there. Why does it look the way it does? I want you to think about what this noise is doing here. Think about what this characteristics of this waveform are, and come up with an explanation for why that gives us this distribution if we take a whole lot of samples from it. So that's still something you'll need to figure out on the assignment. Now, what about multiple sinusoidal electrical noise sources? Well, before we had just the 10 millivolt noise. What happens if, in addition, we had some 5 millivolt noise at a high frequency and 3 contributions of plus or minus 7 millivolts at 3 other frequencies? Well, now we've got 5 different sources. We've got the 60 hertz noise, we've got some other noise here and some other noise here. We're going to have not just one of these sinusoidal noise sources, but multiple ones of those added together to make our N. And I'm going to have to leave that up to you to do the test. But plot it out, make a comparison to a Gaussian, and take advantage of this example that we gave you as part of the assignment package to go and have a look at what the comparison is between the Gaussian distribution and your actual data. So now let's see what's the next step. The next step asks, what is the random uncertainty from your pressure data? And so you're going to read in that array of data that you saved from the lab and take a chunk of that data and see what you can figure out about its distribution. And if you know about the distribution, you should be able to figure out what you'd use as a random uncertainty if you just made a single one of those measurements. The random uncertainty, almost always going to be twice the standard deviation. And then the question is, and if you took 100 measurements while the pressure is steady, what would that give you? Remember that the uncertainty decreases as the number of measurements you average over taken as a square root. So you'd need to apply that. Now here, I've got my own data, and if you don't have any data, you can use my data and do some analysis on that. And then I've converted that data to a floating point array. And if I wanted to, I could plot a histogram of, I want a chunk out of that data array D, and I'm interested in all the rows, and I want column not 0, not 1, not 2. I want column number 3, 0, 1, 2, 3, column number 3. And if I plot that out, there's a histogram that I get by plotting out that data. You'll need to take that farther, along with what you know from the example that we worked on with the TMP36 data, to draw some conclusions about your own data. And that should pretty much wrap up the assignment for you. So I hope this helps out, and I look forward to seeing some good results. And I hope you found it actually enhances your learning to try some of this stuff ahead of time try to figure out what's going on before you get to some additional hints to help you move along the way. I know it's really frustrating, but we've got actual research that demonstrates that that's a really effective way to learn how to do things and remember how to do them. So good luck with your assignment.